hurricane can weaken before landfall and still push more water into a neighborhood than a stronger storm. That sounds backward only because the number beside the storm answers the wrong question. Category describes wind at one part of the circulation. It does not describe the water already moving toward land. On a forecast map, one digit feels complete. Category 1 through 5, a clean ladder from danger to catastrophe, but the ocean does not read that ladder. Water responds to the entire wind field, how long it blows, the seafloor, the coast, the tide, the waves, the rain, and the rivers. Two storms with similar categories can therefore produce radically different floods. One may be compact and fast, crossing deep water toward a steep coast. Another may be enormous, slow, and aimed across a shallow shelf toward a bay shaped like a funnel. The second can pile up much more water with lower maximum wind. The useful question is not simply, what category is it? The useful question is, what system is this storm coupling to? To answer it, we have to leave the eye wall, follow momentum into the sea, cross the hidden landscape below the surface, and watch the coast reshape the final flood. By the end, the surge map and its complicated colors will make sense as pieces of one mechanism. We will see why a lower category does not automatically mean a falling water threat, why local geography matters as much as the storm, and why hurricane forecasts separate wind, surge, rain, and rivers. Start with the category number. Strip away everything we often imagine it contains. No rainfall. No flood depth. No storm size. No storm surge. What remains is a measurement of wind, and understanding how narrow that measurement is changes how every coastal forecast should be read. The Saffir-Simpson Hurricane Wind Scale sorts hurricanes by maximum sustained wind. In the United States, that wind is averaged over 1 minute near 10 meters above an unobstructed surface. Category 1 begins at 74 miles per hour, and major hurricane status begins at Category 3. The scale estimates wind damage. Notice the word maximum. A hurricane is hundreds of kilometers of moving air, yet its category comes from the strongest sustained patch found anywhere in that circulation. It does not average the whole storm or say how wide hurricane force winds extend, how long onshore winds persist, or how much ocean they cross. Storm surge once appeared beside the categories as a rough range. The National Hurricane Center removed those surge descriptions in 2010 because observed surge varies too widely for wind category alone to predict it. Coastline shape, seafloor slope, storm size, speed, angle, and location overwhelm a category to water conversion. Official guidance illustrates the mismatch with Charley and Katrina. Category 4 Charley produced roughly 6 to 7 feet of surge in southwest Florida. Category 3 Katrina produced a peak near 27 feet along part of the northern Gulf Coast. The ranking did not fail. Surge was never one-dimensional. This creates a dangerous trap. When a storm drops from Category 3 to 2, the wind hazard has changed, but water accelerated earlier does not instantly reverse. The wind field may have expanded, and the track may still aim its momentum into a shallow bay. A category downgrade is not automatically a flood downgrade. Replace the latter with a transfer. The atmosphere carries momentum. Friction hands some to the ocean surface. Water then moves until depth, gravity, coastline, rotation, and time determine where that momentum can go. Category is one input at the beginning of that chain, not a verdict at the end. Wind does not scoop the sea into a wall. It drags across the surface. Turbulence and waves transmit stress downward, setting a layer of water in motion. Given enough speed, area, and time, that moving layer becomes a broad rise in water level. Near land, where escape routes narrow, it becomes storm surge. The distance over which wind pushes in one direction is called fetch. A compact storm may contain extreme wind but expose a smaller patch of ocean to that push. A broad storm can apply weaker wind across a much wider area. Category sees the peak. The ocean feels integrated stress over space and time. Forecasters therefore watch the radius of maximum winds and the outward reach of tropical storm and hurricane force winds. Two Category 2 hurricanes can have different footprints. One resembles a tight drill bit. The other is a giant rotating conveyor. For surge, the conveyor can move a much larger volume of water towards shore. In the northern hemisphere, the strongest onshore push often occurs to the right of the track near landfall, where forward motion can add to rotational wind. But the high water zone depends on coastline orientation. Move the track slightly, and a shoreline can flip from offshore wind to onshore wind. Water also has memory. A storm that generated waves and elevated sea level offshore has already changed the starting condition near land. Weakening wind close to landfall does not erase stored motion. Surge can keep advancing while the headline category falls, especially when the large outer circulation remains intact. Our first replacement for category is a moving field, wind strength combined with area, duration, direction, and fetch. That field is not yet a flood depth, it is momentum entering the ocean. The next conversion happens on a landscape most people never see, the continental shelf beneath the storm. In deep water, displaced water can spread through a large volume. The ocean has room to redistribute the disturbance. As the moving mass reaches shallower water, available depth contracts. The flow slows, bunches, and rises. It is a crowd entering a narrowing corridor, except the corridor is the seafloor. Imagine a broad low wedge sliding toward the beach. Across a shallow shelf, friction reaches through more of the water column, and the coast blocks forward motion. Water accumulates faster than it can escape sideways. The surface tilts upward toward land, while the same storm keeps pushing from behind. A gently sloping shelf exposes surge to this compression over a long distance. A steep shelf can keep deep water closer to shore, reducing that long buildup, although local bays and channels may still create severe flooding. Neighboring coastlines can react differently to the same wind field because their underwater ramps differ. Bathymetry, the shape of the seafloor, is part of the hurricane mechanism, not scenery below it. Every ridge, shoal, trench, and shelf changes how water travels. The storm supplies force, but the submerged landscape helps decide how that force becomes water level at the edge of land. When the rising surface reaches dunes, seawalls, roads, or levees, a threshold is crossed. Before overtopping, a barrier redirects water. After overtopping, each additional centimeter can open a new inland route. Flood area grows nonlinearly because a small rise can connect the sea to an entire low basin. Now send the same wind-driven ocean toward two shelves. On the steep coast, much of the disturbance stays lower. On the broad, shallow shelf, water stacks into a taller wedge and crosses the coastal threshold. Same category, different machine. The coastline has turned identical atmospheric input into different outcomes. The Gulf of Mexico makes this hidden control easy to see. Broad stretches of shallow shelf lie in front of low coastal land. Elsewhere, deep water approaches shore more quickly. A hurricane track drawn through the atmosphere may look similar across both, but beneath that line the moving water meets a different ramp. Hurricane Ike reached the upper Texas coast in 2008 as an upper-end Category 2. Its circulation was exceptionally large. Across the shallow northwestern Gulf Shelf, that wind field drove a destructive surge over a broad area. Category described the peak wind but could not express the scale of the water-moving machine. Charley in 2004 had another shape, intense, compact, and fast towards southwest Florida. Its Category 4 winds devastated a narrow path, yet compact size and track limited the surge footprint compared with larger Gulf storms. Stronger at the peak did not mean larger in every consequence. Place the storms side by side without category labels. One has a tight core and small onshore fetch. The other spreads onshore wind across hundreds of kilometers and keeps pushing. For roof damage, peak wind matters enormously. For the volume of ocean being mobilized, size is impossible to ignore. Even within one landfall, surge is patchy. An inlet admits water into a lagoon. A peninsula shields one shore and exposes another. A shoal focuses waves. A dredged channel conducts water inland. Measurements separated by a few kilometers can record different histories because they occupy different paths through the system. The shelf sets the broad stage, but the storm is also moving. Its forward speed and approach angle determine how long each coast stays beneath onshore wind. The mechanism becomes a timing problem, not simply how hard the storm pushes, but exactly where it pushes and for how long. Storm size is not fixed by category. Hurricanes of the same intensity can differ several-fold in the radius of tropical storm force winds. Large storms churn more ocean, generate longer waves, and affect the coast earlier. Their surge threat can span multiple states, while maximum wind occupies a small part of the circulation. A hurricane can weaken at the center while growing outward. Changes in internal structure, eye wall cycles, and surrounding weather can spread wind over a larger radius. The category may step down while the water-driving footprint expands. One hazard decreases at the same time another component becomes broader. Duration matters because the ocean needs time to respond. A fast pass can deliver a sharp pulse. A large, slow circulation can hold onshore wind against the same coast through multiple tide cycles. Each hour maintains the surface slope and prevents accumulated water from draining away. Size does not replace intensity. Stronger wind increases surface stress rapidly. Surge emerges from their combination. A small intense storm, a large moderate storm, and a large intense storm are three different machines. Compressing them to one digit discards the dimensions that distinguish their water response. The practical clue is on the forecast wind field graphic. Look beyond the center point. Expanding colored areas show where sustained winds extend. For water, pay attention to the side producing onshore flow, how much shallow ocean sits beneath it, and how long that sector overlaps the coast. Transform the category badge into a footprint, and the mismatch becomes obvious. The digit remains unchanged, while the wind field doubles in width. The ocean area under stress expands dramatically. The number did not become wrong, it stayed silent about the dimension that changed. Forward speed changes duration and where water accumulates. A slow storm can hold surge against a coast, pour rain over one watershed, and delay drainage. A fast storm shortens exposure, but may add forward motion to winds on one side. Neither speed is universally safer. Each rearranges the hazard. Approach angle determines which coastline faces onshore wind. A storm crossing at a right angle creates one pattern. A storm sliding nearly parallel can sweep water along the coast and into openings far from the center. A small turn can redirect the strongest push into or away from a bay. The skinny center line is not a damage line. The forecast cone represents uncertainty in center position, not the storm's size and not the boundary of impacts. Surge, rain, tornadoes, and wind extend outside it. For coastal water, the orientation of the whole circulation matters. Consider a crescent-shaped bay. With one track, wind pushes water past the mouth and along the outer shore. Shift the center 40 kilometers, and the same rotating wind points directly into the opening. The narrowing bay concentrates flow, and water rises at its head. Landfall timing also selects the astronomical tide beneath the surge. Surge is the abnormal rise generated by the storm. Storm tide is that rise added to the normal tide. If the peak arrives near high tide, the combined level starts higher. Waves then ride on top of both. Our single storm now splits into three tracks. Same maximum wind, same category, same coastline. One drives water offshore. One runs parallel. One aims the onshore sector into the bay at high tide. Only the third crosses the flood threshold. Geometry and timing rewrite the outcome. Coastlines are not straight walls. Bays narrow, estuaries branch, barrier islands break at inlets, and rivers meet the sea through low corridors. When surge enters a funnel-shaped bay, the same volume occupies a shrinking width. Water deepens and can climb farther inland than an open coast estimate suggests. Barrier islands absorb waves and block some flow, but they are not continuous dams. Water moves through passes, over low dunes, and across breaches. Behind them, sounds and lagoons fill from several directions. When wind reverses after the eye passes, water can be driven toward another shore. Rivers complicate the boundary. Surge moves upstream while rainfall runoff tries to move downstream. If the ocean raises the river outlet, drainage slows. The meeting point becomes a traffic jam of water, coastal surge below, fresh water arriving from above, and local rain falling directly on the city. Urban geometry adds another layer. Roads, railbeds, canals, seawalls, and buildings reroute flow. A road embankment may protect one block and deepen water on another. A canal may become a fast inland corridor. Fine-scale elevation determines which thresholds connect first. This is compound flooding, hazards interacting rather than merely adding. Surge blocks drainage, rain fills streets, rivers rise, and waves damage the barrier that was slowing the surge. Each process changes conditions for the others. A category value has no field for these connections. Watch the coast assemble as a network. Open ocean feeds an inlet. The inlet fills a lagoon. The lagoon backs into a river. Rain arrives from the opposite direction. When one low road overtops, 4 isolated blue regions become one connected flood. The decisive event is connectivity, not category. Coastal water during a hurricane has several layers. Astronomical tide moves predictably with the moon and sun. Storm surge raises or lowers the background surface. Waves oscillate above that level and run up slopes. Rain and rivers add fresh water from land. Observed depth can contain all of them. Forecast maps specify a vertical reference for good reason. Water above ground is not water above mean sea level. A 5-foot level over marsh at 4 feet elevation leaves 1 foot above ground. The same level over a road at 1 foot leaves 4. Elevation converts level into local depth. Waves are easy to confuse with surge. Surge is a relatively slow rise across a broad area. Waves ride on that elevated platform, delivering short, violent peaks and erosion. A house may face structural wave damage even where mapped still water inundation depth appears survivable. Rainfall has its own geography and clock. A storm can produce catastrophic inland flooding after coastal surge recedes. Slow or stalled motion magnifies that risk. A weakening wind category can coexist with worsening water because rainfall and drainage follow different rules. When officials say not to use category alone, this is why. Category is not a summary score for the storm, it is one scale for one hazard. Surge warnings, rainfall forecasts, river forecasts, evacuation zones, and local instructions carry information the wind scale intentionally does not. Stack the water layers and street depth appears only at the end. Tide, plus surge, plus wave reach, plus freshwater, minus ground elevation and drainage. The visible flood is the output of a system. No single layer, and certainly no wind digit, reconstructs it alone. Forecasters model surge with tools built for the missing dimensions. One central system is SLOSH, sea, lake, and overland surges from hurricanes. It represents a coastal basin as a grid, and calculates water response to pressure, wind, track, size, speed, bathymetry, and topography. The grid is not just ocean, it extends over low land so water can cross barriers and fill connected areas. Cells vary in size, becoming finer where detail matters. As the simulated storm moves, the model transfers water through the basin, while coastlines and elevations constrain the paths. For planning, engineers do not run one perfect hurricane. They run thousands of plausible storms with different tracks, intensities, sizes, and speeds. Maximum water from families of scenarios can be combined into products called meows and ums. These are envelopes, not depictions of one actual storm. An envelope asks what water could occur across a controlled set of possibilities. An operational forecast asks what is likely from the actual storm with current uncertainty. Both are useful, but neither is a category lookup. They preserve the dimensions the wind scale discards. Models have limits. Small topographic features, waves, rainfall drainage, and rapid changes may require other tools or local knowledge. Forecasts improve as observations update track and structure. A map is not a promise at every doorstep. It is a physically informed range for decisions made before certainty arrives. Now the forecast map assembles from the mechanism. A storm field crosses the shelf. Water moves cell to cell. Barriers overtop. Multiple tracks fan through the basin. The model keeps the highest credible water at each location, revealing a risk surface no category badge could contain. The National Hurricane Center's potential storm surge flooding map expresses water height above ground in vulnerable coastal areas. It combines forecast scenarios and accounts for track, size, intensity, and uncertainty. Its colors are local depths, not a paint bucket spread evenly from the shoreline. Read it by locating your area, checking the legend, and remembering what the color means, potential water height above normally dry ground for that forecast product. Then compare it with evacuation guidance. The map supports a decision. It does not replace local orders or knowledge of access routes. Evacuation zones are not hurricane categories. They are planning boundaries based on surge vulnerability, roads, population, and logistics. A zone can be ordered out during a lower category storm because the expected water pathway is dangerous. An inland location outside the surge zone may still face freshwater flooding. Forecasts evolve. Track shifts change the onshore sector. Wind field growth changes ocean area under stress. Arrival time changes the tide. New observations redirect the ensemble. The correct response is not to anchor on the first category, but to follow hazard-specific products through each update. For a coastal household, know whether you are in a surge or evacuation zone before the storm. No more than one route. Treat official evacuation instructions as threshold decisions, not predictions of exact doorstep depth. Once water reaches roads, the safe decision window may already be closed. Zoom from basin to bay to neighborhood. The broad surge envelope enters 2 inlets, follows a river, and crosses 1 low road. On the final street grid, houses only blocks apart receive different depths. The forecast did not become inconsistent as it zoomed in. Terrain revealed where water connects. A hurricane category measures maximum sustained wind. That is valuable, but it is not a total danger scale. Surge depends on wind field, size, speed, direction, and history. Flooding then depends on shelf depth, coast geometry, tide, waves, rivers, rain, elevation, and the thresholds linking them. The apparently weaker storm can deliver the stronger water disaster. Its circulation may be larger, its onshore push may last longer, its track may align with a shallow shelf and funnel-shaped bay, its arrival may coincide with high tide. The consequence belongs to the coupling, not the badge. The best mental model is a chain of translations. Wind becomes surface stress. Stress becomes moving water. The shelf turns motion into height. The coast turns height into pathways. Local elevation turns water level into depth. Infrastructure and timing turn depth into consequences. Each forecast product watches a different link. Category watches peak wind. The wind field graphic watches footprint. The cone watches probable center positions. Surge maps watch coastal inundation. Rainfall and river forecasts watch freshwater. Evacuation messages combine those hazards with the time needed to move. When category changes, do not ask whether the storm is simply better or worse. Ask which hazard changed, which did not, and what the local landscape will do with what remains. The answer may be reassuring. It may also reveal that the most dangerous part was never represented by the number. The ocean does not arrive at an empty edge. It meets a shelf, a bay, a river, a road, and a city. In that moment, the coast is not merely where the hurricane ends. The coast becomes part of the hurricane's machinery, and that is why the water needs its own forecast.